We are jumping right in today with rubric-based benchmarking and reinforcement learning for advancing LLM instruction following.
Mhm.
This paper really gets at one of the most persistent and, frankly, frustrating gaps in today's large language models.
Yeah, their ability to handle truly advanced, complex instructions, the kind you see in the real world.
Exactly. So for anyone who just needs the one-minute version, here's the rundown.
Okay, so the core problem is that LLMs today, they still fail when instructions get really complex. Think multi-turn conversations or when they have to follow hidden system prompts.
Right. And so the researchers here propose a solution that's really built on two huge contributions. First, a new benchmark called Advanced IF.
And this is a high-quality benchmark. We're talking over 1,600 prompts, all written by human experts.
Designed to be adversarial, which is key. And they come with these incredibly detailed evaluation rubrics.
Then there's the second piece, a new training pipeline called RIFL. That's RIFL.
Which stands for Rubric-Based Instruction Following Learning. It uses reinforcement learning, but, and this is the important part, the reward signal comes directly from those verifiable rubrics.
And the bottom line, it works. RIFL gave the Llama 4 Maverick model a huge boost, a 6.7% absolute gain on that really tough advanced IF benchmark.
Yeah, it took the score from about 51% up to 58. So they basically proved that the rubric can be this central, verifiable tool for both training and evaluation.
Okay, let's unpack this a bit because this really puts the work into context. We've seen reinforcement learning with verifiable rewards, RLVR, work really well in structured domains.
Like math or code generation.
Exactly, things where there's a clear right or wrong answer. But for open-ended text, aligning a model with, nuanced human preferences has always relied on RLHF, which is subjective.
Right, reinforcement learning from human feedback.
And this paper is all about bridging that gap. It's taking the rigor of verifiable rewards and actually applying it to these really complex, open-ended language tasks.
Yeah, you need a reward signal that can scale up for training, but also, perfectly aligns with what a human expert thinks is a good answer.
Which brings us right to section 1. Defining what advanced IF even means.
It's a great question.
Yeah.
Because a base LLM can summarize this article just fine.
Sure.
But real-world tasks just layer constraint on top of constraint. So the Advanced IF benchmark, it identifies 3 critical areas where these models tend to fall down.
And their whole evaluation is built around this taxonomy. So let's break down those 3 areas. First up is complex instruction following, or CIF.
Right.
This is still a single-turn prompt, but it contains 6 or more distinct constraints all at once. Things like format, style, length, and even negative constraints like don't mention X.
Then the second one, which you could argue this is the hardest category, is multi-turn carried context IF. Let's call it CC.
Okay, so CC is all about memory.
Yeah.
The model has to retain and integrate instructions across multiple turns of a conversation. Exactly. And the third is system prompt steerability, or SS. This is about how wide the model sticks to rules set way back in the system prompt.
Things like safety or tone or output format, even when the user's immediate prompt seems to be pulling it in another direction.
That multi-turn example is probably the best way to really get a feel for the complexity. The paper has this great karaoke suggestion scenario that shows just how hard it is.
Walk us through that.
Okay, so turn 1, the user asks for 10 to 15 family-friendly songs. Simple enough.
Yep.
Turn 2, the user adds a new rule. Okay, I like these, but now you have to exclude any songs by the Beatles. So the model has to update its state. It's got the old rules plus this new negative constraint.
And then in turn 3, it gets almost unfairly difficult. The user just says, give me another 15 options. So what does the model have to track to get that one response right?
It's actually 4 distinct things all at once. The response has to, first, still be family-friendly from turn 1. Second, it has to be between 10 and 15 songs. Third, it has to exclude the Beatles from turn 2. And fourth, this is the really tricky one, it has to suggest new songs, not just repeat the ones from the first list.
That level of state retention is just, that's where even the top models really struggle.
And the power of this benchmark is that it uses prompts and, crucially, rubrics that were all made by human experts. These weren't just, machine-generated prompts. They were designed adversarially to find the model's breaking points.
That rigor really shows in the results.
It does. When they tested frontier models like GPT-5 on Advanced LF, the average score was only around 78%, which sounds high, but it's a long way from perfect.
And if you break it down by category, The picture gets even clearer.
It really does. For GPT-5, the score on complex instruction following the CIF part was 87%. Pretty strong.
But its score on multi-turn carried context, CC, just plummeted to 74%.
That 13-point drop. It confirms that managing that sequential context and integrating new rules is the real bottleneck here. That's what needs specialized training.
So the problem is crystal clear, which moves us into Section 2, the RFL pipeline. This is their proposed solution to actually fix this gap.
Right, and RFL is formulated as a pretty standard RL problem. You're trying to maximize a reward, but the reward function itself is unique because it's based entirely on that strict multi-part rubric.
Which raises the big question, right? How do you generate thousands of these high-quality rubrics for training data, and then how do you make sure your verification model, your judge, is actually aligned with human judgment at scale?
Yeah, you can't have a human expert checking every single training step. It's just not feasible.
So that's why RFL has these two major components in its setup. The first one is the rubric generator.
And the generator is an LLM itself, a fine-tuned Llama 4 Maverick model. They trained it on thousands of expert-annotated rubrics to basically automate the process.
And it works surprisingly well.
Extremely well. After fine-tuning, the generator hit an F1 score of 0.790. That's a huge jump from its starting point of 0.639.
So think about what that means for scaling up. They now have a model that can reliably generate evaluation criteria that's almost 80% aligned with what a human expert would write.
It lets them create massive amounts of high-fidelity training data.
So once you have the rubrics, you need the second component, the reliability check.
Yeah.
This is the rubrics verifier training.
The paper makes a great point here. You can't just use a vanilla LLM as a judge. They're just too inconsistent.
So they built this really robust two-stage pipeline to align the verifier. Stage 1 was an SFT stage.
Standard supervised fine-tuning. They used a small, very high-quality golden set of about 5,000 expert-verified data points. These had binary yes-no judgments for each criterion, plus detailed justifications.
Like a chain of thought.
Exactly. And then comes the RL stage, which is the really crucial part. They use RLVR to train the verifier further. And the reward signal here is based on the ratio of agreement between the verifier's judgment and the expert's label.
That ratio of agreement-reward. That seems like the secret sauce.
It really is. Because it forces the verifier, which is acting as the reward model, not just to guess yes or no, but to align its entire justification process with the human's reasoning. It has to learn why a constraint was met or not.
Which makes the final reward signal much more robust. And the ablation study they ran proves this whole process was absolutely necessary.
Oh, completely. The fine-tuned verifier, after that RL stage, hit an F1 score of 0.728.
And you compare that to the baseline. The vanilla Llama 4 Maverick judge started at a pretty sad F1 score of 0.515.
That jump is enormous. It proves the RL step wasn't just, a little extra polish. It was essential for alignment. It put their custom verifier on par with dedicated reasoning models like O3 Mini.
So the reward signal is solid. That brings us to Section 3, which is all about the reward design. How do you actually calculate the final score to best train the main LLM?
Right. Let's dig into the rewards they tested. They tried 3 main ways to calculate the final sequence-level reward.
First was the all-or-nothing reward. This one is the strictest. The model gets a reward of 1 only if it satisfies every single criterion in the rubric.
Miss 1 out of 10, and you get a 0. Very harsh.
The second was the fractional rubric reward. This is more forgiving. The reward is just the percentage of criteria you satisfy. Hit 7 out of 10, you get a 0.7.
And the third was a hybrid reward, just a 50-50 mix of the all or nothing and the fractional score.
So what worked best?
This is a really instructive finding for anyone training these models. The all or nothing reward achieved the best overall performance, 58.1%.
That's fascinating. Why did the fractional reward, which seems like it would provide a smoother learning signal, actually perform worse?
It really comes down to the incentive structure you're creating. With a fractional reward, you're sort of encouraging the model to satisfy the easiest constraints first.
It can coast and still get a decent score.
Precisely. If 7 criteria are easy formatting things and 3 are complex logic, the model learns it can get a 0.7 reward with very little effort. But the all-or-nothing reward, it's punitive. It forces the model to treat every single constraint as mandatory.
Which is what a human user actually wants.
Exactly. That strictness pushes the model toward full, complete adherence.
But the obvious downside of a super strict reward is reward hacking. The paper mentions they saw models generating weird artifacts or these verbose self-evaluations to try and trick the judge.
Classic reward model gaming. Their solution was some pretty clever reward shaping. They just added 2 more universal criteria to every single rubric for the verifier to check.
And what were those 2 checks?
Simple, but really powerful. 1, did the model give a clean response without any weird artifacts or self-talk? And 2, was the response complete, not cut off or truncated?
And they show a great example of this working in the Dragon Party invitation prompt.
Yes, that prompt had all these subtle rules like capitalization and a maximum number of exclamation points.
That when the vanilla model judged it, the LLM output was messy. You would add extra sentences explaining what it did, trying to overconfirm that it followed the rules.
But the output that the final fine-tuned RIFL verifier rewarded was clean. It just did the task, it capitalized dragon, it used only 5 exclamation points, and it didn't add any of that verbose junk. It proves the reward shaping worked.
It guided the model to just meet the content constraints, not to game the judge.
So to sum up the core contribution here, RFL is this really robust framework that uses these structured, human-aligned rubrics to create a verifiable reward signal.
A signal that's actually effective for teaching these complex, generalized instruction-following skills.
It overcomes the limits of both the subjective nature of RLHF and the narrow domain-specific nature of earlier RLVR work. A major step forward.
Yeah, by proving you can automate and align these rubrics with such high fidelity, this research really establishes the rubric as the foundation for the next generation of training and evaluation.
Which leaves us with a final provocative thought. And this is really for you, the researcher or engineer listening, who might be integrating these techniques.
We know that multi-turn carried context, that CC category, is still the single hardest challenge, even for models trained with RAFL. It's all about managing state over a long dialogue.
So consider this. How could you adapt this rubric-based verification to give feedback at every single turn of a conversation instead of just a final reward at the very end?
If you can verify compliance at each step of a dialogue, not just the last one, you might be able to radically accelerate how we teach these models to be truly great conversational agents.